Welcome everybody back to another day of 126. I told you guys on before that I was going to figure something out, and I decided on what I'm going to do. I'm going to make the last page. It has the two problems on there, right? And you only had to do one of them. So in addition to the exam redo, you could attempt the other problem for up to 5 points of extra credit. So if you got a 40 on the exam, right, then 50% back would be 30. So you could get up to a 70. And then if you get the other problem right, you could get up to a 75. So a 40 can go to a 75, a 50 could go to an 80, and so on and so forth. So I'll pass back exams a little later. Please come up to me if you didn't get them so that I can give you your exams. Cool. So once again, you can do the other problem in addition to it to get some extra credits. All right. So where were we? We were on exponential equations. Did I upload the notes for that one? Of course I didn't. I didn't print them off. So I need to actually go. Yeah, I didn't do that. Okay. Sorry for 1 second. Need to do something real quick. Which form I want to be which form. Thank you for your patience. What is a Acorn's favorite math subject? Geometry. Geometry. It's a pretty good joke. Maybe not. Maybe it's terrible. Okay. Then put that back where it belongs. And start it up again. Okie dokie. So we're now going to be talking about a new type of solving. Now that we know about these new operations, we can solve more equations. We can figure out more problems that involve these things. So here are the three cases. You're going to keep working through an exponential equation. Step one is going to be simplify your equation until you get one of the three forms. Form A, which I'm going to highlight in red. Oh. Which is you get b to the something, b to the blue box, equals b to the something else. So they have a common base. Now, sometimes when you get to this format, it might not look like it is in a form A situation, but it is just in disguise. So maybe you get like 3 to the x is equal to 81 to the x minus 4. 81 is a power of 3, so you can reduce it into that format. You'll see a couple examples in a second. Form B is you get b to the something, b to the blue box, equals a to the red triangle. And these are no common bases, no common base. So this would be a situation like you got 5 to the x equals 3 to the x minus 7. 5 and 7 have no common base. 4 and 16 have a common base, a 4 or 2. 7 and 343, they have a common base of 7. 27 and 243 have a common base of 3, so on and so forth. That's why I wanted you to look at these guys right here, these little powers. And the last format would be something along the lines of b to the something equals a number. I'll call this form C. So depending on which form you get into, you're going to solve the form. If you got them being the common base, then all you need to do is set the exponents equal to each other. Set the blue box So once again, highlighting this to make sure it's in the same section. Blue, and then purple. Set the box equal to the red triangle. So in this format, because they're the same base and they're equal, their exponents have to be equal. There's no other way around it. So that's all you need to do in this case. If you have the second case, it's arguably the most difficult, but it's still fine. What you're going to do is what I call, quote unquote, apply ln to both sides to bring down the exponents. To solve. I promise you this will start to make more sense once we actually see these problems in action. And the same thing is true for exponential form C. You're going to apply log base B, quote unquote, to cancel the base. Apply log base B to both sides. To cancel out the base. So we're going to see an example of these each. So the apply log and apply natural log, that thing is not going to make much sense yet. It will make sense very soon. So as an example of form A, I've got 8 to the 3x minus 1 equals 32 to the x. But Phil, that doesn't look like exponential form A. It is, though. But it is. Because 8 is 2 cubed and 32 is 2 to the 5th. Sometimes we need to check for common bases. Sometimes we need to look and see if there are powers of anything. So if that was like 35, this wouldn't be the case. We wouldn't be able to do this. Now, one thing I will say, by the way, is that Form B can solve everything. Form B can solve all of these problems by applying natural log to both sides. It's just sometimes that's making way more work than you need it to be. It can work out. It's just sometimes it's just way too, like, it would have been so much faster just to look at it from Form A standpoint. So, kind of going through the step-by-step process. Step 1, we've got them equal to each other. So that's going to be 2 cubed raised to the 3x minus 1 equals 2 to the 5th raised to the x. We're changing 8 into 2 cubed. We're changing 32 into 2 to the 5th. And so we've got a power raised to a power, which means you multiply the exponents. So this is 2 raised to the 9x minus 3 equals 2 to the 5x. And there's only one way for these things to be equal, is if the exponents were equal. If they're not, if the exponents aren't equal, there's no way for this to work. So we're going to set them both equal to each other. 9x minus 3 is equal to 5x. Subtract the 5 from both sides, add the 3, or however you want to do it. You get 4x is equal to 3, which gets me x equals 3/4. And much like per usual with equations, the greatest thing about them is you can always check your answer. An equation should, if an equation is going to work, when you plug in 3/4, you should get the same number. Now, sadly, if I do this in my calculator, so if I do 8 raised to the 3 times 3/4 minus 1, I get a really nasty number. So if I'm checking it by plugging in to both sides and jotting down the numbers you get. So what I mean by that. So, oh yes, go ahead.
Um, this is just a random idea, but could you take the first number that you get and minus the other one that you do second, like the second time, and if it equals to 0, then
Oh yeah, that'll be true. Yes. So Preston makes a very, very valid point. What you could do instead is you could just subtract this from both sides so that one side is equal to 0, and then plug the x values into to that thing. And if you get 0, you know you did it right. That's a good point. So that's another way to do the same thing. So I plugged in 3/4 into this thing and I got 13.454-ish. So the left-hand side, I got 13.454. And the right-hand side, if I do that, so 32 raised to the 3 divided by 4, lo and behold, I get the same number, 13.454. So I know I did it correctly. But you could also do it by taking the subtraction between the two sides. And if you get 0, you know you did it correctly. So that is a form A situation. It doesn't look like it at first, but it is. So it's dramatically quick. It's dramatically quicker. I want to say drastically and dramatically at the same time. But it's much quicker to do this one. That's why I go over this option. But here is form C, because form B is the biggest one. So solve the equation. 5 times the quantity 2 raised to the negative 4x plus 1 plus 1 equals 16. So at its current stage, it does not look like it's in form C, but we're going to do a bunch of algebra to get it into that format. So step 1, 5 times 2 raised to the negative 4x plus 1 equals 16. I'm going to subtract 1 from both sides. 5 times 2 negative 4x plus 1 equals 15, at which point I will divide by 5 and get that 2 to the negative 4x plus 1 is equal to 3. Now it's looking like a form C because 2 and 3 don't have a common base. Because it's an exponential function equals a number. It's b to the something equals a number, not b to the something equals b to the something else with x's and stuff. So you could apply natural log, but it's actually faster to do it this way. What I'm going to do next is step 2. I'm going to say, what I say is I write apply log base 2. Now, this is for our notes. If we're on an exam or if we're doing this by hand or whatever, we don't need to say apply log 2. We can just write it. But this is for our notes to look at what's happening. I'm going to apply log base 2 to both sides of the equation. Don't write down what I'm writing down because this is incorrect. John Doe student does that. And the problem is that John Doe student wrote something that's not correct. And I will mark down for this because this is not mathematically valid. If you write down the thing that I wrote in pink down here, that is not mathematically valid because log base 2 is an operation on something. If I write it like that, that's saying log base of 3 times log base 2 of blank. And there's nothing to plug into log base 2, so it's not mathematically valid. It's like putting the period in the middle of your sentence or putting a capital letter at the very end of your sentence instead of the start of your sentence. It doesn't make sense. So it always needs to go right here. It needs to go in front, otherwise it's not mathematically valid. And I know you know what you mean, right? Like I get you, and that's why I will only mark off 1 point, which you can then correct on the exam redo to make it only a half a point off. But it is a situation like in an English class or in a history class, if you say the Declaration of Independence was signed in 1777, they're gonna have to mark you down. Not a lot, if especially if your argument's perfect. Even if you write that wasn't signed in 1977, so like I was like -1. Come on, man. Remember. And so that's the justification here is not mathematically valid. So please make sure that it goes in front. Like if you're also confused as to why that's true, like why we have to do this, if I wanted to take the square root of both sides, would I write this? No. I would write the square root before it because I'm taking the square root of something. If I do that, that's saying square root 3 times square root, which doesn't make any sense. So please don't make that mistake. Okay, next thing. The reason why we wanted to apply log base 2 is that, remember, logarithms are inverses of exponentials. And this is the same log, like they have the same base. So these cancel. And this ends up being, put it up here, negative 4x plus 1 is equal to log base 2 of 3. Which doesn't look great at first, but we have to remember log base 2 of 3 is just a number. It's just a number, like you or me, right? It's an irrational number, but it's a number nonetheless. So we can solve for it. We just need to solve for x. So what we need to do, subtract 1, divide by -4, and we're all done. So negative 4x equals log base 2 of 3 minus 1, which equals then x equals log base 2 of 3 minus 1 divided by -4, which is approximately negative 0.1462. And you're going to want to round to whatever the amount of decimal places they want you to round to. The reason why I do about 4 or 5 is that if I want to check my work, trying to plug in log base 2 of 3 minus 1 into this expression seems like a little bit of a daunting task, doesn't it? Like if you try and plug it into your calculator, you'll see that it gets really muddy in the calculator. Like you're putting a fraction inside of an exponent. It looks really nasty. So instead, what you should do is plug in the approximation. And as long as you get really close to the other hand side, you know you did it right. So case in point, if I plug in negative 0.1462 into the equation, 5 times 2 raised to the negative 4 times negative 0.1462 plus 1 in the exponent, then out, and then plus 1. If I plug that into my calculator, I get 15.9983. That's really close to 16. So since I'm using the approximation, I shouldn't get 16 exactly, but I should get dang close, and I did. If I started getting like 13 or 14 or -2, I know I did it wrong. The left-hand side is 15.99. The right-hand side is exactly 16. Any questions on that using your calculator to check your answer? Of course, you could also do what Preston has suggested. You could take this number, subtract 16, and you get negative 0.001, which is basically 0. So it's essentially 0 because we're using an approximation. Cool? Jive, as the kids say, right? No, they don't say that. Okay. Last one. This one is form B. We have 11 to the 6x plus 5 is equal to 7 to the 2x. There is no common base. Form B. Because this isn't an exponential function equals a number, it's an exponential function equals another exponential function. So this is where we use natural log. For more, like we could use natural yeah. So I'm going to rewrite it. So step one is already done. So step two, we're going to apply ln. So ln of the left-hand side equals ln of the right-hand side. Natural log of 11 to the 6x plus 5 is equal to natural log of 7 to the 2x. Now we're using natural log because they don't have a common base. There's not like or something like that. And ln is the fastest one to write. And so you can really squeeze it in there instead of doing log base 11 or log base 7, which you can do, or you can even use log, like the common logarithm. It doesn't matter. It's just natural log is the fastest one to write. That's the reason why we use it, honestly. So the whole point of this is that this allows us to bring the exponents down because that's one of the big properties of the logarithms. And by the way, in case it's been a while, it's been a week or 5 days. But the reason why we can do this is by this fact we had up above. If you have two things equal to each other, then you can take the logarithm both sides. And if you take the log, and if two logs are equal to each other, then the insides are equal. So the point being with that one is that we can, like, if we have two things equal, which we do right now, they're equal to each other, we can take the logarithm, any logarithm of both sides. So the whole point, though, is that this allows us to take this and bring them out front. So what we've got now is parentheses 6x plus 5 times natural log of 11 equals 2x times natural log of 7. Any questions so far? Yes.
So when it doesn't have a base, it will become LN.
Uh, there will always be a base in these problems.
So like in that problem, like,
The previous one?
yeah, since it doesn't have a base. It
So like it does have a base involved. It has the 2, log base 2. Yes. So if there was like, what do you mean if there was no base? If it was 2x instead of 7? Then that becomes, oh, good question. Good question. If you have 11 to the 6x plus 5 equals 2x, that is a much more challenging question to answer. Because there's not really a way to really go about solving it nicely. I mean, there probably is some algebra you can do to manipulate it. Let me think. Get back to you on that one. That one's one of the ones where I would honestly either use a method of approximation, which there's a couple things that mathematicians have created to approximate zeros, or you'd have to graph it to find the intersection points of those two things. Very, very difficult. But good question. Fun problem to do. I mean, I might just look at this and have a fun time this weekend doing that problem, right? That's what we do for fun on the weekend, right? Nick, you do that during the weekend? You just solve random math problems? Really? Tiernan? Yes? No? Okay. Wow. I'm the outlier. Legitimately, my wife and I we found this video on matrices, and it describes something that we never heard before, like a way to interpret matrices better. And we said, no, there's no way that's true. And so we spent the entire Friday proving it to ourselves. So that's a fun day at the cookhouse there. Anywho, say what? Yes, we did. It was like it was a situation like why the heck weren't we ever taught this when we were learning linear algebra? It's a very, very fascinating concept about the determinant. But if you get to linear algebra and you want to know about it, email me. Linear algebra is math 253. So if you ever take math 253, talk to me and I can tell you an interesting interpretation of the determinant. Okay. Anyways, so this looks scary. But it's just a Canadian goose, right? We talked about Canadian geese and how you can just puff up your chest and scare them away. It's trying to be intimidating, but the fact of the matter is natural log of 11 and natural log of 7, they're just numbers. How would you so if you're looking at that and it's scaring you, how would you solve this? Well, you distribute the 11 in, you get the x terms by themselves and solve. This is literally a linear equation. It just doesn't look nice because it has natural log of 11 and natural log of 7. So, point being is we can distribute that natural log of 11 into the other two pieces. Orange. And so what we've got is 6x natural log of 11 plus 5 natural log of 11 equals 2x natural log of 11. Sorry, natural log of 7. And just like with the linear equation, you want to get the x terms on one side. So we can either bring them to the left or bring them to the right. It's your call. What do you guys want to do? You want to bring x's to the left or to the right? I'm fine either way. Or does it truly not matter? That's the correct answer. It truly does not matter. So I'm going to bring it to the left and bring the 5 natural log of 11 to the right. I get 6x natural log of 11 minus 2x natural log of 7 equals negative 5 natural log of 11. And here, there is a common factor of x. That we can take out front. We can factor it out. And we'll go from writing 2 different x's to only a singular x on the outside. So this becomes x times the quantity, 6 natural log of 11 minus 2 natural log of 7 equals negative 5 natural log of 11. At which point we'll divide both sides to get our final answer, which is x equals negative 5 natural log of 11 divided by 6 natural log of 11 minus 2 natural log of 7, which is approximately negative 1.1423. Any questions on that? Okay, so small note on it is that you could have done the method we use in Form C. You could do that too. You could apply log base 11 or log base 7 to make it nice and neat, because if you use one of those bases, one of the things is going to completely cancel out. So I've done both of them here. If you use log base 11, so if you don't mind, I'm going to zoom in. If you didn't finish writing, don't worry. I'm going to zoom back out in a second. If you use log base 11, then on the left-hand side, the 11's canceled. So all you got is 6x plus 5 times 2x log base 11 of 7. You can bring the 2x log base 11 of 7 over to the left-hand side, bring the 5 over, and then factor out the x. And you get this answer, which is very similar, just a little bit different. and you get the same number. So it's the same thing. That's the nice thing. Or you could do it in the reverse option. You could use log base 7, canceling it out on the other side, distributing the log base 7 in, or log base 7 of 11 in, and solving it that way. Either way will work. I find the ln to be the best way because it just makes it's easier to write. It takes less space, and I find it to take less time. But that's my experience. You could find that it's way faster to use log base 7. It's your call. Any questions on this? Yes, Tiernan.
So you took the natural log in the beginning,
Mm-hmm.
so you just took it of 11, and you did both sides. So you just same for log. You just take log of 11, do the same thing, just both sides.
Yep, just both sides.
Different.
Yeah.
It's a different base, I guess, the log.
Because with the log base 11 or log base 7, it will cancel out one of the bases on the exponential functions.
Oh, all right.
Which makes it look a little bit nicer in some regards, but worse in others. All right. So that's how we solve exponential equations. They fit into like all of them that you'll experience, at least in this course, will fall into one of those 3 categories. So then we have logarithmic equations. We got exponential and logarithmic equations. So step 1 is to simplify with the help of log properties, which is section 3.4. That's why I wanted you guys to make sure you did all your homework and practice those a little bit before today. To get it into either one of the 2 forms below. You can either get log base b of a blue box equals log base b of a red triangle. That is going to be log form A. And then log form B is if you get log base b of a blue box equals a number. You get one of those 2 forms. You won't get different bases. You won't get log base b of something equals log base a of something else, because that's a much more awful monster. That requires using the change of base theorem, along with a couple other things. It won't be fun. These ones are fun. So we focus on the fun. All right. So if you're in form A, then by that property, if you have a log of something equals log of something else, then the insides have to be equal. Set. So for log form A, you're going to set the blue box equal to the red triangle and call it good. Whereas if you're in log form B, use the remembering trick to convert to exponential form. And that's page 1 of what? What page was that? It's page 1 of the unit 3.3 notes. Let me check real quick. Sorry, 1 second. I'm coming right back to it. 3.3. And the remembering trick was note 3 on page 1 of 3.3 notes. 1 on unit 3.3 notes. Just in case you don't remember what, like when you're referencing this, what's the remembering trick? Okay. So here's the problem, though. Herein lies the rub. The solutions that come from these equations are the possible solutions. Since you can't plug in 0 or negative numbers into logarithms, you may get what we call an extraneous solution. It looks like it's an equation. It looks like it's a solution, but it's not. It's kind of like a mirage, right? Like we see these in the desert. We live in the desert. There's things you think it's there, but it's not actually there. And the same idea is that this is a solution that worked only because we applied some weird rules and things got a little bit haywire. We experienced this when we talked about solving square root problems, right? Because when you square both sides of an equation, you fundamentally change it. Anything that was negative is now positive. And so you get possible new solutions that don't work. Same thing with rational expressions or rational equations. You might multiply by the LCD, which might throw things off a little bit. So you get extra solutions that don't actually work. So this one is not optional. Step 3, this is not optional. You need to check your answers in the original equation before you did any manipulations for a myriad of reasons. One, you don't want to plug it in into a later equation because that's when you started to get involved. And we are human, we make mistakes. So plug it into the original one so that it's in its most purest form. And as said in the note above, just be on the lookout for zeros or negatives on the inside of a logarithm. If you've got a negative on the inside of a logarithm, immediately done. Straight to jail, right? So, log form A. Right now, it does not look like it's in form A, so we have to convert it to it. Step 1. So we're going to look at that log of x, and I'm going to highlight this plus here. Equals log of 5x minus 7. So, because of the properties of logarithms, I can take that addition on the outside and condense. I can combine these things. By properties of logs. Unit 3.4. You can combine these things and leave a little bit of space and then write log of x times x minus 3 equals log of 5x minus 7. And just so that we don't have to rewrite another step, we can just write above this, this is x squared minus 3x. Right? So now that we've got them equal to each other, they've got the same base. They're both common logs. They're both base 10 logarithms. So step 2 now gets involved. Step 2, we set them equal to each other. We've got x squared minus 3x equals 5x minus 7. And we can solve that. That's a polynomial equation. We bring everything to one side, factor, set equal to 0. Call it good. So subtract the 5x, add the 7. We get x squared minus 8x plus 7 is equal to 0. And that factors to x minus 1 times x minus 7 equals 0. If this type of problem shows up on an exam or on a quiz and you're not getting a nice factorable thing, it's a good indication that it was probably a little error made. So then that means that the possible solutions are x equals 1 and 7. So step 3 is to check our work, check answers. Unless there's any questions on anything I've done so far. So typically this is going to be done in your head because all you're really looking for is just making sure that the logarithms are defined. If you're confident in your algebra, then as long as they can be plugged into the logarithms, you're good. So I'll check x equals 1 and I get log of 1, that's fine, plus log of 1 minus 3 if it was me right now, I would stop and say, I know that it's not going to work, but I'm going to write out the whole thing just so we see it. Does that equal log of 5 times 1 minus 7? And you'll see that both of these are issues. Because we can't have negatives inside the logarithms. So I immediately, if it was me, I'd immediately stop right at the second logarithm because I knew going into it, plugging it into my head, 1 minus 3, that's -2. It's done. There's no need to check. We're all already good. We've figured that out. So I wouldn't even continue. That make sense? So that's all you could, like, you don't have to go through and check everything. As long as one thing fails, that piece is going to be undefined, which is going to be a problem. Granted, the other thing that's nice about it, though, if you want to, you can always plug it into your calculator, plug in the left-hand side, you'll see that you get math error. And remember, math error means that what you're trying to do is not mathematically possible. Syntax error means that you plug in something that the calculator didn't understand. So then I'll try x equals 7. Log of 7, that's fine. Plus log of 7 minus 3, that's log of 4, that's fine. Does that equal log of 5 times 7? That's 35 minus 7, that's 28. And yes, it does. So the answer is x equals 7 only. I don't think I've talked about that in this class yet. If you see me write that on a solution guide or on like for an answer key, when I say only, the answer is technically just x equals 7, but I write the only to symbolize there were other solutions that did end up coming up, but they were not correct solutions. So if you see that on the exam review and it says x equals 7 only, it means that there was another solution or multiple other solutions that did not work. Any questions on that? Okay. Sometimes you get two solutions that work. Sometimes you get both solutions. Sometimes you get one solution. Sometimes you get no solutions. It all depends. It's not always guaranteed that the smaller one's not going to work. So you have to check it each time. There's no convention here. There's no like rule that we can learn. It's just making sure that it does not make a negative number inside a logarithm. So let's do some more examples. So let's go ahead and solve this log form B. So 3 log base 2 of x squared minus 5x minus 6 plus 7 is equal to 16. So there's only one logarithm, so there's no need to combine things. So we get, I don't want to write this down. Did I want to write the step price? Yeah, I wanted to start the step-by-step process. Step 1 is to get into the proper format. So I'm going to subtract 7, and that gives me 3 log base 2 of the quantity x squared minus 5x minus 6 is equal to 9. So that tells me that log base 2 of x squared minus 5x minus 6 is equal to 3 when I divide both sides by 3. Therefore, how do we convert this one? So since it's in logarithmic form, we can convert to exponential. So step 2 is to start with the base, work your way across the equal sign, and then back over to give us 2 to the third power is equal to x squared minus 5x minus 6. And so that will give me x squared minus 5x. Negative 6 minus 8, that's minus 14 is equal to 0. And that will factor nicely. Again, that will factor to x minus 7 times x plus 2. And so that gives me the possible solutions. X equals 7 and negative 2. Step 3. Unless there's any questions so far. So now, from now on, I'm going to be checking it in my head. So plugging in 7. 7 squared, that's 49 minus 35. That's going to be 14 minus 6, that's 8. That's good. We're fine. Plug in negative 2. We've got 4 plus 6, or sorry, 4 plus 10, that's 14. Minus 6, that's 8. That's fine. So step 3, check in head / calculator. Check the insides of logs in head / calculator. And x equals 7 works out. X equals negative 2 works out. So this is actually the answer. Okay. Let's see here. If you end up getting a situation where one works and the other doesn't, I've had plenty of students do this so they don't have to rewrite the whole thing. They just cross out the one and then box this. That's fine with me. If you want to cross it out and just write X like that, that's fine. Just whatever you want to do it, just to make sure that there's only one true choice. No problem. Okay. In the interest of time, we're going to bleed over. We're definitely going to need to take some time on Wednesday to finish off this. By the way, our exam is coming up. What time? What day? It's coming up next Monday. I'll be posting an exam review very soon with the stuff to study for it. So we'll get to that soon enough. I want to do a couple of these. I didn't do any of those ones. I need to add one of those in here. I don't like that I have to do that, but okay. Let's do part A. So let's do this one, and then we'll do one more of the and we'll do C. We'll do A and C, and then maybe I'll post the video solution to the rest of it. So for this one, we've got that minus sign. We can combine that into division on the inside. This becomes natural log of y minus 4 is equal to natural log of y plus 6 divided by y. You could have brought the natural log of y, you could have added it to the other side so that you could do multiplication instead, but it doesn't matter. I would assume if it was me, if I was a student in this class, I would probably do that first. And so I want to encounter this situation and show you what to do. So since they're both equal to each other, you can set the insides equal to each other. So that means that y minus 4 is equal to y plus 6 divided by y. And how do I solve that? Well, one of the things, so if you're ever encountered with a situation you've never seen before, think about what you could do. What would be a good idea? Cry? Probably. That's a good one. It's always a good option. So like multiply by y?
The y on the bottom, and that cancel out one on top.
Ah, excellent thing. I'm glad you brought that up. So that is something we cannot do because that is trying to cancel a term with a factor. We can only cancel factors vertically. So that won't work. But I think Nick was going to say multiply both sides. Yes. So we can always multiply both sides to get rid of the fraction. So that cancels it on the right-hand side. And I get y squared minus 4y is equal to y plus 6. And that will factor nicely. That'll become y squared minus 5y minus 6 is equal to 0. That gives me y minus 6 times y plus 1 is equal to 0, which gives me the possible solutions. Y equals 6 and -1, but you'll find out that -1 does not work. If you plug that into the first thing, you immediately see that it doesn't work. Natural log of -1 minus 4, that's natural log of -5, it doesn't exist. So the answer is just y equals 6 only. Now you might be wondering yourself, Phil, you multiplied by a variable. Isn't that a bad thing? What if y was 0? Well, y can't be 0 just by the statement alone, the equation. If y was 0, then this would be undefined. So we're able to multiply by y without having to worry too much because it wouldn't work in the original problem anyways. All right. Yes, Nick.
Three problems where the answer would be solution. Both of them are extreme.
That is correct. Yes. So it could be the case that you get two negative solutions, like two solutions that don't work, in which case the answer is no solution. It's rare, but it can happen. It's like I'd say once every like 15 to 20 problems, you might find one, but it's few and far between. And on exam, I'd say that would be a little bit of a rude thing to do. That's a little cheap shot. So if you're getting no solution, that's probably an indication on the exam that you're not doing, like you made an error somewhere. All right. And then we'll do 8 minus 5x, 5e to the x 15 equals 2. So we're going to try and get it into exponential thing equals a number. Because there's no other, like, e is the only base that I see, and there's no e squared or like common base with e here. So we'll bring the -2, we'll bring the -8 over. We get -5e to the x plus 15 is equal to -10, or sorry, -6. That gives me that e to the x plus 15 is equal to 6/5. So this just so happens to be the one case where if you apply natural log of e, you get the right answer. Like you don't have to do any real extra work. You apply ln of both sides, and realistically on an exam, you could just write it in, like squeak it in. I've had plenty of students write like, so ln on this side's no problem, but then they write like ln like that. That's fine on an exam. But since we're doing this for our notes, and this is something we're going to look back over, so this is natural log of the left-hand side. So natural log of e to the x plus 15 equals natural log of 6/5. And lo and behold, natural log and e, they do cancel. And so I get x plus 15 is equal to natural log of 6/5. So x is equal to natural log of 6/5 minus 15, which is approximately -14.8177. And then I'll round it based on whatever decimal points they want. Usually the convention is 2 decimal places, but every once in a while, people like to throw their own little happy tree in there and do their own way. Okay? Yes, Glacier.
I
Mm-hmm.
still -5.
Mhm.
What happened to the -5 on the 6?
So they canceled out. So we're going to divide both sides by -5. and the negative signs cancel each other out. Cool. All right. I will post a video, guys, for you to finish off the rest of them. I'm going to switch over to 3.6 because we do need to go over that. I forgot to upload it to my this thing, so I'm going to need to do that real quick. 1 second. Pause the record. Okay. So now that we know how to solve exponential equations, now we can solve for other things. Before, we were only able to solve for the variables that weren't in the exponent, but now we can solve for variables that are on the inside of a base or in the exponent of a base, an exponential base. So just as a reminder about these formulas, the compound interest formula is that A is equal to P times the quantity 1 plus R divided by N raised to the NT, where R is the annual percentage rate as a decimal. In decimal form. And then the continuously compounded interest formula is A is equal to PERT, so P times E raised to the RT. It doesn't need to be, since it's compounded continuously, the end value is infinity, and you'll see that it actually ends up being that. And then there's the exponential growth and decay formula, which is that Y is equal to Y naught E to the RT, where R is the relative rate as a decimal. Growth implies R is positive, and decay implies that R is negative. And then T is measured in time, so most likely hours or minutes or seconds. Whereas with the compound interest formula and the continuous compound interest formula, time is always measured in years. And then we had percent growth and decay, which what's going on here? Wait a minute. What's the difference between these two things? Because this one should be, it should be the same formula, isn't it? Isn't it the same formula? Sorry, I'm tripping. 1 second. Cool. Okay. My apologies. Oh, and on picture mute. There we go. Percent growth is P is equal to P sub 0 times 1 plus R raised to the T, where R is the rate of increase or decrease as a decimal. Increase implies R is greater than 0, and decrease implies R is less than 0. So you will not need to memorize these formulas. They will be provided. So you don't have to have them memorized, just know how to use them. And so you might be wondering, well, we already went over this. We went over this in 3.2, but the difference was we didn't have logarithms before, so we weren't able to solve for the unknowns in the exponent or the inside of the logarithm or inside of the base. So now we need to know how to utilize equations, logarithmic equations, to find these things. So, and then as a little reminder about these types of problems, words of wisdom is that application problems, there's no one way to solve them. You'll get halfway through a problem and realize that you made a wrong assumption, so you have to start over again. When I do math problems, it usually takes me 2 to 3 drafts before I get to the final answer. I have to erase a lot of stuff. And so I need to incorporate it wherever I need to. So I go back a few steps in my work, sometimes even restart the problem completely and retry. The key thing is to never give up. Always have tenacity. And to quote Thomas Edison, which I never learned from Thomas Edison, but I learned it from the great classic Nick Cage movie that is a national treasure, the National Treasure, the movie The National Treasure. And so I didn't fail. I just found 10,000 ways to not that wouldn't work. That's okay. You can learn by not learning things. So a myriad of examples. Example 3.6.1. The value of a home in Nevada has increased by a remarkable amount each year. That's true. That's very, very true. Using the data from last year and assuming trends continue exponentially, the estimated value of your home, V of t, V for value, T for time, can be modeled by the function V of t is equal to 385,000 times 1 plus 0.07222. Now, I actually did this when I made this thing. I looked at the percent increase that year and assumed that it was going to continue. And so we're assuming it's measured in the years starting in 2017. Answer the following problems. The initial estimated value, that's the initial amount. So the initial estimated value is, so this is a percent increase problem. It's P is equal to P sub 0 times 1 plus R raised to the T. So the initial estimated value is P naught, which equals $385,000. Good luck finding that in Vegas nowadays. Insane what happened. Thank you, COVID. No, more specifically, thank you, hedge funds. Thank you, people for buying up properties and not giving them to families. That's really okay. It's a great thing to do to people. Anyways, growth or decay rate, it's a growth rate. And 1 plus R is equal to 1.0722. So R is going to equal 0.0722. And usually when we talk about the rate, like if we're talking about it by itself, we want it in percentage form. So 7.22%. Any questions so far? Part A, what is the projected cost of the house in 2026? So a common mistake that students will make is they'll plug that in. They'll do 385,000 times 1.0722 raised to the 2026, which will get you an obscenely large number. And the problem is it's not measured that way. Time isn't measured since the dawn, since BCE, before the Common Era. It's going to be measured since 2017. So the T value for 2016 will be 2026 minus 2017, which is 9 years. Right? 9 years. So what we're really trying to find here is we want V when T is equal to 9. So V of 9 is 385,000 times 1.0722 raised to the 9. And let's plug that into our calculator. 385,000 times 1.0722 raised to the 9th. We get a whopping total of $721,012.77 if we round to the nearest 2 decimal places, which makes sense. I get to make that joke as many times as I want because it's the funniest joke ever. Not actually. But. So this home is basically doubled in value in 9 years. Is it really worth $700,000? Is a house ever really worth $700,000? No. It's obscene. It's bloated. It needs to be blown up. The whole system. Just throw it out. Light it on fire. Start over. Okay. Part C. Unless there's any questions on that one. That one we could have done beforehand. We could have done this from in unit 3.2 and we would have been fine. But then this one will require what we just learned. In which year will the house reach an estimated value of $450,000? So what this is asking, and this is what you always want to do when you're looking at a word problem, is ask yourself, what are you trying to find? I'm trying to find a year. I'm trying to find a time. So we want T when V is equal to 450,000. So we can solve that. 450,000 equals 385,000 times 1.0722 raised to the t. So the good news is this is an exponential equation, and we're just going to solve it like any other equation. We want to get the variable by itself. So I should probably start off by dividing by 385,000. Not a pretty number, but it's a number nonetheless. And that cancels it on the right hand side. 450000 divided by 385,000. I get 90 over 77. I recommend just writing it in a reduced fraction. Don't write an approximation. These things get really, really messed up by approximations. So this reduces down to 90 over 77 equals, leave a little bit of space and then write 1.0722 raised to the t. And so this is a form C. Form C. You can write that down if you want to. It's form C from the last one. It's a number equals an exponential function. B to the blank equals a number. That's what this is. So you could do it in two ways. You could apply natural log. You could apply a natural log, or you could apply log base 1.0722. However you want to do it, it's fine. You guys want to do natural log or log base 1.07222? Natural log. That's probably the convention. So apply ln. Natural log of the left-hand side equals natural log of the right-hand side, which allows us to bring down this exponent and get that natural log of 90 over 77 equals t times natural log of 1.0722. Solving for t, we get that t is equal to natural log of 90 over 77 divided by natural log of 1.0722, which is approximately natural log of 90 divided by 77 divided by natural log of 1.0722 is 2.237-ish, 2.238 years. But that's not the answer. Because the answer is not saying how many years, it's saying in which year. So in 2019, 2017 plus 2.238 is 2019.238. So in 2019, it will reach 450,000. That is the answer. Let's talk about that once you've written it down. And so we will, I think we might have enough time to do one more example. But if not, we'll finish this off on Wednesday. And then I'll be sending out an email with a link to watch the rest of the lecture, the examples. I'd encourage you to do them on your own time. They're good practice problems. But point being, so in 2.238 years from 2017, it will reach that. So it's asking in which year it will happen. So it'll happen about 0.238 times 12. It'll happen in the end of the end of March. So after March, it will reach 450,000 if the trends continue. All right, any questions? So now you can use logarithms to solve these problems. So another example. I think this one good. So two random people named Cloud and Eris Don't know, I found those names off the internet, I was having fun. Not sure anybody, like, there's no relation to any game or anything like that. McLeod and Eris are putting $7,000 into a savings account that is compounded continuously for their newborn son. The goal is to give this as a gift in 22 years. What annual percentage rate is needed for the account to grow to 50,000 when it's given as a gift? Well, kid's gonna get that gift, but Eris is gonna die. So that's a highbrow joke right there for anybody who plays Final Fantasy. That's a good joke. Okay, so what type of equation are we going to be using? The compounded continuously. That is the dead giveaway. So use A is equal to PERT, P-E to the RT. So there's no one way to solve them, but we can identify all the things that we need. We know what A is. A is the total amount. It stands for the total amount or the final amount. So we want it to be 50,000. A is going to equal 50,000. P is the initial or the principal amount. Principal, which I think to call makes way worse. It's called the initial. And that's how much they initially put in, which would be 7,000. E is just a number. This is the one thing that people get all tripped up on. E is the irrational number E, the natural base, 2.71-ish. So E is not something we need to solve for or find. It's just a number. R is the unknown because it says what percentage rate, what APR is needed. And then T, bless you, is equal to 22 years. So utilizing all this information, we've got 50,000 equals 7,000 times E to the R times 22. So we're going to solve for this one. We need to solve for the rate. So we need to get the rate by itself. The first thing to do would be to divide both sides by 7,000. And that will reduce down to 50 over 7 is equal to E to the 22R. And we think to ourselves, man, I really don't like the fact that that's in the exponent. If there was only some way to bring down exponents, if there was only some type of thing that we've learned that can bring exponents from the top into being multiplied, natural log. So apply ln. Natural log of the left-hand side equals natural log of the right-hand side. Natural log of 50 over 7 is equal to natural log of E to the 22R. And because it's natural log, it cancels out the E because they're the same base. Natural log is log base E. So the E cancels. Let's use orange. We can use orange yet. So this gives us that 22R is equal to natural log of 50 divided by 7. So R is equal to natural log of 50 divided by 7 divided by 22, which is approximately 0.089 ... And so it didn't specify, let's just round it to 2 decimal places, but we want to write it as a percentage rate. We want to write it as a percent. So 8.94%, approximately 8.94%. And if you can get a 9% interest rate, please let me know. I'd love to sign up with that bank. I guess you could always put your money in the stock market and make a gamble. Sp25 or whatever is supposed to increase like roughly 10% each year. So I mean, I guess that's what you could do, but that is assuming that things don't go crazy. But any questions on that one? Okay, that'll do it for today. If you didn't get your exam, please come up so I can hand it back to you. You guys have until Wednesday. Since I didn't announce that thing about the exam redo, I handed back on Wednesday of last week, correct? So let's make it do, like ideally I'd like it Wednesday, but if you need a little bit extra time, you can bring it back on Monday of the next week on exam day. But I'd rather you get it back done sooner rather than later, so, via. Stop recording. If you guys have any questions, feel free to email it. Otherwise, have a great day. Write your congress people.